So, let's do lecture 3-4 on simulation in the transient response performance consideration chapter. So many control systems are not in the class of those we have described analytically, first or second order and without zeros. I don't know why I wrote poles there, without zeros. In order to evaluate their transient performance, regardless of how well they are approximated by the analytic solutions from below, or from before, we will simulate their step responses. So that's kind of what we're going to do in this lecture. I'm going to do a demo in MATLAB, essentially, or show you all of the code that you need to do this in MATLAB. And I'm going to... I'm pretty confident I'm going to get a MATLAB classroom or a computer classroom for the final exam, so you can use MATLAB in the final exam. Because a lot of the design problems we're going to do going forward are orders of magnitude easier to do in MATLAB. Python would work too, but people got mad at me when I was using Python. So MATLAB people prefer, seemingly, for this control stuff. Oh, my battery is going. Shoot. Pause. Let me grab my charger. So fast. Oh. All right. Here we go. I got more battery while I was gone. That was cool. How does that work? Okay, so what? I plugged it in. Okay, so this is available on the internet. If you go to my website, if you go to the text, if you go to control, and then you go to the source page, and you will find the transient response performance simulation, which has the MATLAB code that's the source for this lecture. It's executable, but set save figures to 0 because there is a little hook here for saving the figures, and I use this function MATLAB to TIKZ, which exports the figure using this function. It's on the MATLAB, whatever their file exchange website is. You can get this function if you want, but it's not built into MATLAB. So it'll give you an error if you don't set save figures to 0. But anyway, so go ahead and get that, and yeah, so that is the source for it. MATLAB has several built-in control system and control system toolbox functions for analyzing the transient response of a system represented by a transfer function system model. We'll explore a few here. Consider, for instance, a closed-loop transfer function with this being the expression. So notice that second order, but it's got a 0 here, and z is what's representing the 0. So where z is some real 0, we'll move around later. Omega n is some given value, 20 pi, and the damping ratio is 0.3, so it's underdamped. Let's explore the system's transient response. Clearly, for large negative values of z, the response should be approximately congruent with the exact analytic solutions of lecture 3.2. Specifically, the rise time will be described by figure 3.3. The peak time will be here. So these were the formulas that were given in lecture 3.2, and that figure is right here. So, all right. And good. So let's compute these analytic values. So I just define zeta, omega n, the damped natural frequency. I had to use, I couldn't compute it directly. I had to use the graph for the rise time. So if I look here, this is figure 3.3. I look up our damping ratio, and it corresponds to a TR omega n of about 1.3. I guess it was 1.39, I think I said. I don't know. Since this is equal to, so say 1.39 is equal to TR omega n, which is the vertical axis here, then I can solve for the rise time as being 1.39 divided by omega n. So that's how I got that formula, and then I just wrote it in MATLAB syntax there. And then the peak time, percent overshoot, and the settling time, and I just go ahead and print them out. So notice how I did this. I said, using the second order approximation, this is what we predict, right? So this is all just the analytic prediction from the second order approximation. Notice that depending on what that zero is, might not be a good approximation. Okay? So this, we're going to want to compare this to what we actually compute at the end. All right? So let's define the transfer function object. So I'm going to do something that's a little bit more of an advanced feature here, and it's because you guys have seen how to define a system like I have in the past. Sys equals TF, where then I put in the numerator and denominator coefficients. You guys have seen the state space, where I put in the A, B, C, D matrices. You guys have seen even, I think, ZPK, where I put in the zeros, the poles, and a gain. All of those work to define a system in MATLAB, and we can use those systems to, we can simulate those systems for their transient responses as follows. But I wanted to do something a little bit different. There's this more advanced object called the model array, and you can initiate one by using the stack function. And this is a typo too. So for each zero location. So what we're going to do is we're going to define an array of zeros, ZA, that's going to be at different places in the complex plane. So we have our, our second order pole pair, okay, zeta of 0.3, let's say it's around there. And remember that according to this, according to this relationship here, this is negative, let's see. Yeah, it's negative zeta omega n. I was going to try to bring it back from before, but it won't come back. So this is negative zeta omega n. And we're going to want to put that zero in some different places related to where those poles are. So that's why I put them at negative zeta omega n times three different places. I'm going to put them 1.5 times, put it 1.5 times out past those poles. And then I'm going to put it at 3 times. And then I'm going to put it at 5 times. Okay? And I want to see, for these 3 different zero locations, how that step response unfolds. So I use TF to define each of these with the different zero locations. So I just loop through each zero location. I define a transfer function. I store it in this model array F. Okay? So now I've got a model array F that's got 3 different system definitions, one for each of those 0 locations. Okay? So this is going to be the first one, this is going to be the second one, this is going to be the third one. Okay. For a step input, an initial value of 0, let's simulate, which is the case that we used to characterize the transient response, right? That was under the definition of the transient response performance characteristics, we used this as our situation. Step input and 0 initial conditions. So the step function would be the easiest way to solve for the step response. So MATLAB's got a step function, step, that works pretty well. However, we choose the more general LSIM for demonstration purposes because I want to show you guys different tools and not just always use the easiest tool for everything. So LSIM is a little bit more advanced. It allows you to simulate for a transfer function you've defined or a state space model that you've defined. You can simulate the response of a system to an arbitrary input and initial conditions. So let's define a linear space, a time array from 0 to 0.3 seconds, 100 points. So this is time. And I'll define the input to just be 1 at every value of time. Okay? So that's what this does. It defines there to be a 1 at every value of time. So that gives us the input at each time value, which is LSIM requires that you give it the input at each time step. And then the initial condition is 0. And I go ahead and pre-allocate my array for the output to be, so for each of these 0 locations, I want to have an output simulation. So I go through, I loop through, I do an LSIM, I give it that system, I give it the input, I give it the time array and the initial condition, and I just loop through and get the output for each. And I end up with these 3 solutions. So when the 0 is at negative 28, which is the closest one, notice that we're way up here. I mean, just eyeballing this, the percent overshoot is over 100%, right? So it goes over 2, whereas it settles to 1. So it's going to be over 100% overshoot here. This one's going to have, 60% overshoot, and this one's closer to 50% overshoot. Notice that our analytic response for the overshoot said it was going to be 37%. So this 0 is really screwing that up, right? It's messing up our percent overshoot estimate significantly. And it very much depends on the location of the 0. Okay, if you push that 0 further out, that approximation gets better. Okay? Okay, this indicates that the 0 location definitely matters and the deviation is worse the closer the 0 gets to the poles. Quantifying the response characteristics is tedious visually, but MATLAB has a built-in tool that helps, step info as a function. So if we were going to go through and be like, okay, what is the settling time? We have to look at what are the bounds, plus or minus 2%. When's the last time each of these goes in the bounds? And what is that time value? That's really tedious to do. And if you wanted to look at what the rise time is, you got to say what's the 10% and what's the 90%. Like these things are tedious to do visually. However, if you use MATLAB's built-in step info function, it will return a struct from which we can extract the rise time, peak time, overshoot, and settling time. So you give it that step response simulation result, and it'll just go through and approximate each of these parameters for you, which is pretty nice. And then I just print it out. So this gives you a way to print out a table nicely, and you can see here the rise times, peak times, percent overshoot, and settling time for the different 0 locations. Notice that the percent overshoot is very affected by the 0 location, and so is the rise time. Peak time and settling time, not as much. Yeah.
So the zero location would be like how aggressive of a damping effect, like in a wheel system? Or how big of a spring?
So, goodness. Well, it depends on how the input enters the system effectively. Where does the input enter the system? How does it enter the system? So it's hard to make a general statement. In a mechanical system, you're going to get zeros essentially when you have differentiation of your input that happens. So zeros emerge from differentiation of the input. There are a lot of different situations that can arise where you have that. So if you've got like, I don't want to make a general statement there because I would not be totally confident in that statement. So yeah, it doesn't necessarily. I mean, you can have springs and dampers and not have any zeros, but there are certain configurations in which it does arise with springs and dampers. I think it's. I mean, I don't want to say. I think it's when you have forcing directly on a spring element and not a mass element. I think that arises then. I think that it also arises when you have displacement forcing on a damper element, but I don't know for sure if that's always the case, so I would have to look into that before I could give you a good answer. So the zero location drastically affects the overshoot and rise time, but it has relatively little effect on the settling and peak times. The takeaway here is not so much the specific result, like where the zero is affects, and this is the quantitative amount, but the tools one can use to find such results and the importance of doing so. So this second order approximation results from here, they didn't do a great job. I mean, let's compare the other ones, 0.02, 0.05, for TR and TP, 0.02 and 0.05. They weren't awful, but they're off by a significant factor for the zero at negative 28, by a factor of 2 for these zeros further out, and then maybe 50% off for the peak times. So the analytic prediction, the second order approximation, it got us close, like in the ballpark, and not so much on percent overshoot though. Percent overshoot's pretty significantly off, right? So when you have this situation, our peak time, settling time, percent overshoot that we can use from our analytic predictions are just okay. So we need to do the simulation like this to check. Now, we don't have to necessarily simulate like all these different possible zero locations or whatever, but we do need to do that for at least one and see what it is. So if we have a design where we place that zero in some location, we need to check in that location, what is my actual settling time? What is the simulated settling time at least? And that's very important to do. Otherwise, you end up in quite a bit of trouble if you've got this assumption that you're going to have a settling time that's 0.1 seconds, but it's actually 0.2 seconds. Well, you missed your mark by 100%, so that's significant. So this is a cautionary tale that once you leave the analytic approximation zone, we can't really trust those predictions, and it gives you also tools for evaluating what the actual performance characteristics are. So being able to use, LSIM, STEP, TF, STEP info, these are things that you guys are going to need to be able to do to evaluate your performance criteria. So this lecture shows you how to do it in pretty significant detail, so hopefully that helps you quite a bit. And you can get the M file from the website. You can also copy and paste from this file to the PDF. So, all right, see you guys on Friday.